In about 4.5 billion years, the galaxy you're part of is going to collide with another galaxy. The collision is already happening. It's been happening for the past billion years and will continue to happen for the next several billion. But here's the thing that's hard to wrap your head around. Even though two galaxies are colliding, even though hundreds of billions of stars are involved, you almost certainly won't notice when your solar system gets torn apart by tidal forces. That's not because the collision isn't violent, it's because space is so incomprehensibly vast that even in a galactic collision, the probability of any two individual stars actually hitting each other is essentially zero. That's what's about to happen to us. Our Milky Way galaxy is going to collide with Andromeda. And to understand what that means, you need to understand Andromeda, what it is, how big it is, how close it is, and why this collision will reshape the entire galaxy we live in. Andromeda isn't some distant, exotic object in the far reaches of the universe. It's our neighbor. It's the closest major galaxy to the Milky Way. On clear nights, if you know where to look, you can see it with the naked eye. It's the most distant object visible to the unaided human eye. When you look at Andromeda, you're seeing light that has traveled 2.5 million years to reach you. You're seeing Andromeda not as it is now, but as it was when your species was just beginning to walk upright on the African savanna. But Andromeda is so much more than a pretty target in the night sky. It's a galaxy of extraordinary complexity, a massive spiral galaxy containing over 1 trillion stars, with a structure that reveals the fundamental physics of how galaxies work. It's a galaxy that has consumed dozens of other galaxies over billions of years. It's a galaxy that's moving toward us at about 110 kilometers per second, and it's pulling our galaxy with it through the fabric of space-time. This is the story of Andromeda, the sister galaxy that will eventually become the same galaxy as the Milky Way. It's a story of distance, of structure, of cosmic collisions, and of what it means for humanity that we live in a universe where entire galaxies collide, merge, and transform over timescales that dwarf human imagination. Let me start with the most basic question. What is Andromeda? Andromeda is a spiral galaxy. That means it has a disk of stars orbiting around a central bulge with spiral arms trailing out from the center. The disk contains most of the young, hot, blue stars and most of the star-forming regions. The central bulge contains older red stars and is dominated by gravity. The whole structure is held together by gravity, with stars orbiting around the galactic center in roughly the same way planets orbit around the sun, though the timescales are vastly different. Andromeda is enormous. The disk is about 220,000 light years in diameter. To put that in perspective, the Milky Way is about 100,000 light years in diameter. Andromeda is more than twice as large as our galaxy. The mass of Andromeda is estimated at around 1 trillion solar masses, though some estimates go higher. The Milky Way is somewhere between 100 billion and 2 trillion solar masses, depending on which mass estimate you use. The estimates vary enormously because measuring galactic mass is extremely difficult. But by most measures, Andromeda is the dominant member of what's called the local group, the cluster of galaxies that includes the Milky Way and about 80 other galaxies. Andromeda contains an estimated 1 trillion stars. That's 1 million billion stars. Each of those stars is a potential home for planetary systems, for the complexity and richness of worlds orbiting them. The number is so large that it breaks human intuition. If you tried to count to 1 trillion, counting one number per second without sleeping, it would take you over 30,000 years. The light we see from Andromeda is the light emitted by those trillion stars, plus dust that blocks some light, plus various emission lines from gas clouds and star-forming regions. The light that reaches our eyes began its journey toward us 2.5 million years ago. When that light started traveling toward us, Homo habilis was just beginning to make simple stone tools in Africa. Humans in their modern form hadn't evolved yet. Civilizations hadn't been built. Writing hadn't been invented. Writing invented itself while that light was traveling towards us. Agriculture was discovered while that light was in transit. The internet was created while that light was still crossing the space between our galaxy and Andromeda. The distance to Andromeda, 2.5 million light years, is almost impossible to visualize. The nearest star to Earth besides the Sun is about 4 light years away. To travel 4 light years at the speed of the fastest object humans have ever built, the Parker Solar Probe, moving at about 400 kilometers per second, would take about 3,000 years. Andromeda is over 600 times farther away than the nearest star. To travel to Andromeda at the Parker Solar Probe speed would take over 1.8 million years. But understanding Andromeda's distance required one of the most remarkable intellectual achievements in the history of astronomy. For most of human history, the nature of Andromeda was unknown. For centuries, astronomers debated whether Andromeda was even a separate galaxy or just a nebula within our own galaxy. The story of discovering Andromeda's true distance is a story of how astronomers, through careful observation and clever reasoning, revealed the true scale of the universe. In the early 1900s, the prevailing belief among astronomers was that the Milky Way was the entire universe. Everything visible in the night sky was thought to be part of our galaxy. There were fuzzy objects called nebulae visible through telescopes, but these were thought to be clouds of gas within the Milky Way, not separate galaxies. The debate about the nature of nebulae came to a head in 1920 with what's called the Great Debate. Harlow Shapley, who had recently measured the size of the Milky Way and determined that the Sun wasn't at the center but toward the edge, argued that nebulae were gas clouds within our galaxy. Heber Curtis argued that at least some nebulae were separate island universes far beyond the Milky Way. The debate was resolved by observations, but not immediately or conclusively. It took photographs from the largest telescope in the world at the time, the 100-inch Hooker telescope on Mount Wilson in California, and the brilliant analysis of those photographs by an astronomer named Edwin Hubble. Hubble did something ingenious. He observed a type of variable star in the Andromeda Nebula called a Cepheid variable. Cepheid variables are stars that brighten and dim periodically. In 1912, an astronomer named Henrietta Leavitt had discovered a relationship between the brightness of Cepheid variables and their period of variation. If you observe how quickly a Cepheid variable brightens and dims, you can calculate how intrinsically bright it is. If you know how bright it actually is and how bright it appears to be from Earth, you can calculate its distance. Hubble identified Cepheid variables in Andromeda and measured their apparent brightness and their periods. He calculated their distances. The distances were enormous, far too far to be within the Milky Way. The Cepheid variables in Andromeda were millions of light years away, far beyond any known part of our galaxy. This discovery meant that the Andromeda Nebula wasn't part of the Milky Way at all. It was a separate galaxy, a separate island universe existing far beyond our own galaxy. The universe was suddenly vastly larger than anyone had thought. Overnight, The universe became a million times larger. Hubble's measurements showed that Andromeda was roughly 900,000 light years away. Modern measurements using different techniques have refined this distance to about 2.5 million light years. The distance is larger than Hubble calculated, but the fact that Andromeda was a separate galaxy far beyond our own galaxy was correct. This discovery is arguably the most important observation in the history of astronomy. It revealed that the Milky Way was not the universe. It revealed that there were billions of other galaxies beyond our own. It revealed a universe of almost incomprehensible vastness and complexity. Now let me describe the structure of Andromeda in detail, because its structure reveals something profound about how galaxies work and what forces shape them. Andromeda, like the Milky Way, has several distinct components. There's the galactic disk, where most of the stars are concentrated in a thin, rotating structure. There's the galactic bulge at the center, a spherical or slightly flattened region where older stars are concentrated. There's the halo, an extended region of sparse stars surrounding the disk. And there are the spiral arms, where star formation is particularly active. The disk of Andromeda contains most of the young stars. These are massive, hot blue stars that haven't lived very long, in cosmic terms. The disk also contains most of the gas and dust. New stars are constantly forming in the disk as gravity pulls gas clouds together, compressing them until fusion ignites. The disk is rotating. Stars orbiting in the disk complete one orbit around the galactic center in about 225 million years, for stars at the sun's distance from the galactic center. Closer to the center, stars orbit faster but complete their orbit in less time. Farther out, stars orbit more slowly and take even longer to complete an orbit. This differential rotation is what creates the spiral arms, density waves that move through the disk, concentrating stars and gas temporarily. These density waves are where most of the star formation occurs. The bulge of Andromeda is different from the disk. The bulge contains older, redder stars. These are stars that formed billions of years ago and have used up much of their fuel. The bulge has very little gas and dust. The interstellar medium is much thinner there than in the disk. The stars in the bulge have random orbits rather than circular orbital paths like stars in the disk. At the very center of Andromeda is a supermassive black hole. All large galaxies appear to have supermassive black holes at their centers. The black hole in Andromeda has a mass of about 140 million solar masses. It's larger than the black hole in our galaxy, Sagittarius A star, which has a mass of about 4 million solar masses. Wait, that doesn't sound right. Andromeda is much larger than the Milky Way, but its black hole is much larger. That might seem right, but the relationship between black hole mass and galaxy mass is more complex than simple proportionality. It suggests that black hole growth and galaxy growth are not simply proportional to each other, and that the mechanisms controlling black hole mass in galaxies are subtle. The halo of Andromeda is even more mysterious than the bulge. It's a sparse region containing old stars and globular clusters, ancient spherical clusters of densely packed stars that orbit the galactic center. The halo extends far beyond the visible disk, containing dark matter that we can infer exists from the dynamics of the galaxy but cannot directly observe. The mass of dark matter in the halo likely exceeds the mass of all the visible stars combined. Andromeda contains about 15 satellite galaxies that orbit it. The most famous are M32 and M110, which are visible in modest telescopes and appear as fuzzy spots near Andromeda in the night sky. These satellite galaxies have been partially disrupted by tidal forces from Andromeda, with stars being torn away. Some of these disrupted satellites are in the process of merging with Andromeda. Over billions of years, Andromeda will completely absorb its satellite galaxies, and their stars will become part of the Andromeda galaxy. This process of consuming smaller galaxies is crucial to understanding Andromeda. Andromeda hasn't grown to its current size just from the formation of stars within it. It's grown by consuming other galaxies. Galaxies in the local universe are not static. They're constantly merging, colliding, being torn apart by tidal forces. Andromeda's history includes dozens of galactic mergers. The evidence for this is written in Andromeda's structure: streams of stars torn from previous mergers, multiple disks at different orientations suggesting the merger of different galaxies, and the halo of old stars that likely came from destroyed galaxies. Now let me discuss one of the most profound aspects of Andromeda: its motion. Andromeda is not stationary relative to us. It's moving toward us at about 110 kilometers per second. That's 250,000 miles per hour. It's approaching us quite rapidly on cosmic timescales. This motion was discovered by Vesto Slipher in 1912, before Hubble had even determined that Andromeda was a separate galaxy. Slipher used spectroscopy, analyzing the light from Andromeda to measure its motion. The fact that Andromeda is approaching us has profound implications. Combined with what we know about the distance to Andromeda and the velocities of both our galaxy and Andromeda, astronomers have calculated that a collision between the Milky Way and Andromeda is inevitable. In about 4.5 billion years, Andromeda will be close enough to the Milky Way that the tidal forces will begin to significantly distort both galaxies. The spiral structure of both galaxies will be disrupted. Stars will be torn from their orbits and ejected into space. The disks of both galaxies will be stretched and warped. Over the course of several billion years, the two galaxies will merge. Their stars will become mixed together. The supermassive black holes at the centers of both galaxies will eventually merge. The result will be a single elliptical galaxy, a featureless, roughly spherical collection of stars without the distinct spiral arms or disk that characterizes spiral galaxies. This collision is not a disaster for life or civilization, at least not for the vast majority of the universe. Even though hundreds of billions of stars are involved, the probability of any star actually colliding with another star during the merger is incredibly small. The distances between stars are so vast that even though the galaxies are ripping each other apart, most stars will never come close to another star. However, the collision will dramatically alter the orbits of stars. Stars that are currently in stable circular orbits around the galactic center will be ejected into the halo, sent on highly elliptical orbits, or even ejected from the galaxy entirely. The solar system could be ejected into the halo, ending up far from the center of the galaxy, receiving much less radiation from distant stars. Or it could be unaffected, remaining in a region of the galaxy that doesn't get significantly disrupted. The future of Earth and humanity billions of years from now will depend on where the solar system ends up when the collision occurs. For context, 4.5 billion years is much longer than life has existed on Earth. Life has been around for about 4 billion years. Humans have been around for less than 1,000,000 years. Civilization has been around for less than 10,000 years. In 4.5 billion years, the course of evolution on Earth will be completely unrecognizable. Humans, as they exist now, will no longer exist. Evolution will have transformed whatever life remains into unimaginable forms. The human species, if it survives at all, will be so different that calling it human would be misleading. So the Andromeda collision, while dramatic and significant, is something that will affect beings billions of years in the future who will be so different from us that the connection to humanity will be tenuous at best. Let me now discuss what Andromeda actually looks like when you observe it, because seeing Andromeda with your own eyes or through a telescope is different from reading about it or seeing simulations. To the unaided eye, Andromeda appears as a fuzzy, elongated blob in the constellation Andromeda. It's not bright enough to see from cities with significant light pollution, but from dark skies, it's easily visible and has been known since ancient times. The ancient Persian astronomer Abd al-Rahman al-Sufi described it in 964 CE as a small cloud in the night sky. From a dark sight, Andromeda is impressive. It covers an area of the sky larger than the full moon. The bright central region is visible to the naked eye, but the outer disk extends far beyond what's visible to the eye. Photographs can capture much more of Andromeda's extent than the human eye can see, revealing the spiral structure, dust lanes, and subtle variations in brightness. Through binoculars or a small telescope, Andromeda is even more impressive. The central bulge becomes distinct from the disk. Dark dust lanes become visible, obscuring the light from stars behind them. The satellite galaxy M32 appears as a distinct fuzzy blob nearby. In large telescopes or long exposure photographs, Andromeda's structure becomes breathtaking. The spiral arms become distinct. Individual star clusters become visible. The dust lanes create a complex structure of light and dark. The overall impression is of a beautiful, intricate structure, a swirling disk of billions of stars arranged in elegant patterns. What you're actually seeing when you look at Andromeda is the light of over 1 trillion stars. Each of those stars is a distant sun with the potential for orbiting planets, moons, and possibly life. The faint light reaching your eye has traveled 2.5 million years through the vacuum of space. Photons of light have been traveling since before modern humans existed, carrying information about stars and their light across the vast distances between galaxies. This thought is genuinely profound. When you observe Andromeda, you're looking back in time. You're seeing what Andromeda looked like 2.5 million years ago. Everything in Andromeda that you observe has changed in the time since that light left. Stars have lived and died. Planets have orbited their stars. Supernovas have explosively destroyed stars. Yet the light that left Andromeda 2.5 million years ago is just reaching us now. The photography of Andromeda has improved dramatically over the past century. In Edwin Hubble's time, the photographs were grainy and low contrast. Modern telescopes, including the Hubble Space Telescope, have captured detailed images of Andromeda showing its structure in unprecedented detail. Each new observation reveals previously unknown structures and details about the galaxy. Now let me discuss some remarkable features and regions of Andromeda that deserve special attention. The disk of Andromeda has multiple components, which suggests that Andromeda has undergone multiple major mergers with other galaxies. There's what's called Disk 1, the main disk of stars. There's also evidence for other disks at different orientations, hints that previous galaxies that merged with Andromeda had their stars incorporated into Andromeda, creating additional layers and structures. The stellar halo of Andromeda is particularly interesting. It contains thin streams and shells of stars, evidence of disrupted galaxies that merged with Andromeda at different times in the past. These streams of stars show the paths that they took as they were torn away from their original galaxies by tidal forces. By studying these streams, astronomers can understand the history of galaxy mergers that shaped Andromeda. One of the most dramatic features of Andromeda is Giant Stellar Stream 1, a collection of stars that traces a long arc through the halo of Andromeda. This stream is thought to be the remnant of a smaller galaxy that merged with Andromeda about 2 billion years ago. The gravitational forces of the encounter tore the galaxy apart, and its stars now form this distinctive stream in the halo. The star-forming regions of Andromeda are where new stars are being born. These regions are concentrated in the disk and particularly in the spiral arms. Giant molecular clouds, huge clouds of gas and dust, collapse under their own gravity, fragmenting into smaller regions where individual stars form. These star-forming regions are visible as bright, bluish regions in photographs and images of Andromeda. Andromeda contains multiple types of star clusters. There are open clusters, relatively loose collections of thousands of stars that are gradually dispersing as they orbit the galactic center. There are globular clusters, dense, spherical collections of hundreds of thousands of old stars that orbit the galactic center in the halo. Andromeda has over 400 known globular clusters, making it much richer in globular clusters than the Milky Way. The supermassive black hole at the center of Andromeda is surrounded by a dense concentration of stars called the nuclear star cluster. This is a region of extraordinarily high stellar density, with millions of stars packed into a region only a few light years across. The dynamics of this region are complex, with stars orbiting at high velocities in response to the gravity of the central black hole and the collective gravity of all the stars in the cluster. Let me discuss the observations of Andromeda across different wavelengths of light, because what you see depends on what wavelengths you're observing. In visible light, the light the human eye can see, Andromeda appears as I've described it. A disk of stars with a bright central bulge, spiral arms, and dust lanes. The blue light comes from young, hot stars concentrated in the disk and spiral arms. The redder light comes from older stars concentrated in the bulge. In ultraviolet light, Andromeda looks different. Ultraviolet light is emitted primarily by very hot, young, massive stars. Ultraviolet observations of Andromeda reveal the star-forming regions particularly clearly. The most intense star-forming regions stand out as bright ultraviolet sources. In infrared light, Andromeda appears different still. Infrared light penetrates through dust that blocks visible light. Infrared observations can reveal the distribution of dust in Andromeda and can show sources of heat that aren't visible in regular light. The supermassive black hole in Andromeda's center emits some infrared radiation as matter falls toward it. In radio waves, Andromeda emits a different signature. Radio emissions come from various sources: synchrotron radiation from electrons spiraling in magnetic fields, emission lines from cold gas, and other processes. Radio observations of Andromeda reveal the distribution of gas in the galaxy and can show structures that aren't visible at other wavelengths. In X-rays, Andromeda appears as a collection of point sources, mostly binary star systems, where a neutron star or black hole is pulling material from a companion star, heating it to millions of degrees and causing it to emit X-rays. The central black hole of Andromeda also emits X-rays. Each of these different wavelength observations gives a different perspective on Andromeda. By combining observations across the spectrum, astronomers build a comprehensive picture of the galaxy's structure, composition, and dynamics. Now let me discuss the history of civilization's understanding of Andromeda. This history is fascinating and reveals how our knowledge of the universe has grown and changed. Ancient astronomers were aware of Andromeda. Abd al-Rahman al-Sufi, a Persian astronomer in the 10th century, described it as a small cloud and noted that it could be seen in the night sky. European astronomers in the Renaissance were aware of a nebula in the constellation Andromeda, though they didn't understand what it was. As telescopes improved, astronomers observed Andromeda in more detail but still had no idea what it was. Some thought it was a gas cloud within the Milky Way. Others speculated that it might be a separate world of stars, but this was just speculation without observational evidence. The turning point came in the early 20th century when Edwin Hubble observed Cepheid, variable stars in Andromeda, and calculated their distances. This provided definitive evidence that Andromeda was far too distant to be part of the Milky Way. Andromeda had to be a separate galaxy. In the following decades, astronomers studied Andromeda extensively. Photographs revealed its spiral structure. Spectroscopy revealed its motion toward us. Observations at different wavelengths revealed different aspects of its structure. The discovery of satellites of Andromeda expanded the picture. Astronomers found numerous smaller galaxies orbiting Andromeda, being gradually consumed by tidal forces. The discovery of the supermassive black hole at the center of Andromeda came later, as techniques for detecting such objects improved. It was identified through the dynamics of stars orbiting very close to the galactic center. The discovery of multiple streams of stars in the halo of Andromeda revealed the history of mergers that shaped the galaxy. By studying these streams, astronomers could reconstruct something of Andromeda's past, the galaxies it had consumed, the times at which these mergers occurred. Understanding Andromeda is not a finished project. Each new observation, each new technique reveals new details and raises new questions. Large telescopes being built now and in the future will be able to observe even fainter structures and more distant objects, continuing to expand our understanding. Let me now discuss what Andromeda means to us, to human civilization, and to our place in the universe. Andromeda is our nearest large galactic neighbor. It's close enough to study in detail, yet far enough away that it remains distant and alien. It's similar enough to the Milky Way that we can use it to understand our own galaxy. By comparing the two, we learn how galaxies work. Yet it's different enough that each difference teaches us something new. Andromeda is a reminder of the vast scale of the universe. The 1,000 billion stars in Andromeda dwarf the billions of stars visible to the naked eye from Earth. Andromeda itself is just one galaxy among an estimated 200 billion galaxies in the observable universe. Each of those galaxies contains billions of stars. The scale is incomprehensibly large. Andromeda is also a reminder that nothing in the universe is static. Galaxies aren't permanent, unchanging features of the cosmos. They're dynamic systems that merge, collide, are torn apart, and reform. In a few billion years, the Andromeda Galaxy will cease to exist as a separate entity and will merge with the Milky Way to form a new galaxy. That new galaxy will eventually merge with other galaxies. Over timescales of trillions of years, all the stars and galaxies will eventually be consumed by black holes or radiated away as thermal energy, leaving a cold, dark universe. This might sound depressing, but it's actually profound. It means that the universe we see now, with its stars and galaxies and life, is a temporary phase in a vastly larger cosmic story. We are living in a golden age of stars and galaxies. We have the privilege of existing when the universe is rich and complex, when stars are shining, when life can exist. Billions of years in the future, the universe will be fundamentally different, older, colder, darker. We are lucky to live now. Andromeda connects us to this cosmic story. When you observe Andromeda, you're observing one of the major features of the observable universe. You're observing a galaxy that contains trillions of stars, any of which could host planets and possibly life. You're observing an object that will eventually collide with our galaxy, merging our cosmic home with Andromeda's in a cataclysmic but slow-motion collision. The light you see from Andromeda has traveled 2.5 million years through the universe, carrying information about a distant galaxy to your eyes. That light has been traveling since before humans evolved, carrying its message across the universe to be observed by a conscious being on a small planet orbiting an ordinary star in the Milky Way. That's what Andromeda is. It's a trillion-star galaxy, a cosmic monster by terrestrial standards, yet dwarfed by the vastness of the universe. It's our nearest large neighbor in the cosmos, yet so distant that its light takes 2.5 million years to reach us. It's doomed to merge with our galaxy in a collision that will reshape both. It's a reminder of the scale of the universe, the processes of galaxy formation and evolution, and the fact that we live in a universe far grander and older and more complex than humans can easily comprehend. Let me discuss the satellite galaxies of Andromeda in greater detail because they reveal a lot about galactic dynamics and the process of galaxy cannibalism. M32 is one of Andromeda's two brightest satellite galaxies. It's a compact elliptical galaxy, a small, dense collection of stars arranged in a roughly spherical shape with no clear galactic disk. M32 is believed to have been a larger spiral galaxy at one time, perhaps similar in size to Andromeda or the Milky Way. But gravitational interactions with Andromeda have stripped away M32's disk and outer regions, leaving only the dense central core that we observe today. This process, called tidal stripping, shows us what happens to galaxies that venture too close to a much larger galaxy. M11O, also called NGC205, is a dwarf elliptical galaxy, a smaller collection of mostly old stars. Like M32, M110 is being torn apart by Andromeda's tidal forces. The outer stars of M110 are being gradually pulled away from the galaxy, disrupted by Andromeda's gravity. Over billions of years, M11O will be completely consumed, and its stars will merge with Andromeda's halo. This process is happening to other satellite galaxies of Andromeda as well. There are approximately 15 confirmed satellite galaxies orbiting Andromeda, though the exact number depends on how we define galaxy versus a chance grouping of stars. Some of these satellite galaxies are so small and faint that they've only been discovered relatively recently, and larger ones continue to be discovered as observational techniques improve. One particularly interesting satellite is Andromeda 14, discovered in 2006. It's one of the least luminous satellite galaxies of Andromeda, containing only about 4 million stars, still a billion times more stars than the total human population, but incredibly sparse compared to major galaxies. The existence of such faint satellite galaxies was not predicted by many galaxy formation models, so their discovery has forced astronomers to reconsider their theories of how satellite galaxies form and survive. The tidal disruption of satellite galaxies creates distinctive features in Andromeda's halo. Tidal tails, long streams of stars, extend from disrupted satellites as they're pulled toward Andromeda. These tidal tails can sometimes be observed in photographs of Andromeda, appearing as faint wisps of stars, extending far from the galaxy's main body. The most famous of these structures is Giant Stellar Stream 1, which I mentioned earlier. This stream appears to be the result of a major merger that occurred approximately 2 billion years ago. A galaxy, perhaps 10 to 20% the mass of Andromeda, collided with Andromeda and was torn apart by tidal forces. Its stars are now spread out in an elongated arc in Andromeda's halo. By studying this stream in detail, astronomers can understand the orbit of the galaxy that merged with Andromeda and can reconstruct something of the properties of that destroyed galaxy. There are additional shells and streams in Andromeda's halo beyond Giant Stellar Stream 1. These structures show that Andromeda has undergone multiple major mergers throughout its history. Each merger event adds a layer of structure to the halo, sometimes dense shells of stars, sometimes elongated streams, depending on the orbital dynamics of the encounter. By counting the number of major mergers that Andromeda has undergone, astronomers can estimate how much mass Andromeda has acquired through galactic cannibalism versus how much has been formed through star formation within the galaxy. Current estimates suggest that perhaps 20 to 40% of Andromeda's current mass came from the merger of smaller galaxies. This process of galaxy growth through mergers is thought to be a major mechanism for galaxy evolution. Small galaxies merge to form larger galaxies. Larger galaxies merge to form even larger galaxies. Over billions of years, the universe's galaxy population evolves, with small galaxies disappearing as they're consumed by larger ones, and the largest galaxies growing ever larger. Now let me discuss the collision between Andromeda and the Milky Way in more detail, including what astronomers have learned from detailed simulations. The collision between our galaxy and Andromeda won't happen suddenly. Instead, it will be a process that takes several billion years and involves multiple close approaches before final merger. About 4.5 billion years from now, Andromeda will have approached close enough to the Milky Way that the mutual gravity between the two galaxies will cause noticeable distortions. Both galaxies will begin to be stretched by tidal forces. Andromeda's disk will warp and distort. The Milky Way's disk will begin to bulge and twist. This phase might last for several 100 million years. Eventually, Andromeda will pass close to the Milky Way, potentially close enough that the two galactic disks actually pass through each other. This would be an extraordinarily violent event. Stars would be ejected from their stable orbits. Gas would be heated and compressed, potentially triggering a burst of star formation. The supermassive black holes at the centers of both galaxies would draw closer to each other. After this first close approach, the two galaxies might separate again, moving apart due to their orbital motion and gravitational interactions with other galaxies. But gravity would eventually pull them back together for additional passes. During each close approach, the structure of both galaxies would become increasingly scrambled. The spiral arms would be torn apart. The disks would become increasingly disrupted. Eventually, after multiple encounters over a span of billions of years, the two galaxies would merge into a single combined system. The final result of this merger process would be a giant elliptical galaxy. The merger simulations show that the combined spiral structure of Andromeda and the Milky Way would be completely destroyed. The disk of stars would transform into a more or less featureless, spherical or ellipsoidal shape. The new galaxy would be much larger than either Andromeda or the Milky Way is now, probably containing around 4 to 5 trillion stars. This new galaxy would probably be given a name by future astronomers. Some have jokingly suggested names like Milkomeda or Andromedky Way to reflect its mixed heritage. But whatever name it receives, it would be a fundamentally different galaxy from either of its parents. The supermassive black holes at the centers of Andromeda and the Milky Way would also merge. Before they merge, they would orbit each other in a close binary system, eventually losing energy through the emission of gravitational waves. As they spiraled inward toward each other, they would eventually collide and merge into a single supermassive black hole with a mass of about 4.1 billion solar masses, the sum of both black holes. This merger of supermassive black holes would release tremendous energy in the form of gravitational waves. The gravitational waves would carry away momentum from the merged black hole, potentially knocking it off center from the merged galaxy. A kicked black hole might recoil away from the center of the galaxy, creating an offset between the black hole and the galactic center. Detailed simulations of the Milky Way Andromeda collision have been performed using supercomputers. These simulations track the gravitational interactions between billions of particles representing stars and gas, following the evolution of the system over billions of years. While there's uncertainty in the initial conditions and parameters, the simulations consistently show that the final result of the merger is a large elliptical galaxy with little remnant disk structure. One interesting aspect of the simulations is that they can predict what will happen to Earth and the solar system. Depending on how close the sun's region gets to regions of dense stars and on how the tidal forces affect the solar system's orbit, the sun might end up in a very different location in the final merged galaxy than it is now in the Milky Way. In some simulation scenarios, the solar system is ejected far from the center of the merged galaxy and ends up in the outer halo, far from most other stars. In other scenarios, it might remain closer to the center. In particularly unlucky scenarios, the solar system might be pulled into a highly elliptical orbit that brings it much closer to the galactic center than it currently is. The radiation and energetic particles emanating from the galactic center would affect any planets orbiting the sun in these different scenarios. If the solar system is ejected far into the halo, it would be much colder, and planets would receive far less radiation from distant stars. If the solar system remains closer to the center, it would be warmed by more stellar radiation. Now let me discuss the observational evidence for past mergers in Andromeda's history. The clearest evidence for Andromeda's history of mergers comes from studying the streams and shells of stars in its halo. Different streams have different ages. Some are very young, in cosmic terms, perhaps a few billion years old, while others are older. By dating these streams, astronomers can establish a timeline of when Andromeda collided with and consumed smaller galaxies. Another line of evidence comes from the multiple disk components that appear to exist within Andromeda. If Andromeda were a simple galaxy that had grown only through internal star formation, it would be expected to have a single, coherent disk. Instead, observations suggest there are multiple disks with different properties and possibly different orientations. This is best explained by Andromeda having incorporated the remains of previous galaxies, with each merger adding a new disk component. The satellite galaxies of Andromeda also provide evidence of ongoing mergers. The fact that there are so many satellite galaxies some of which are currently being disrupted and consumed, shows that the process of galactic cannibalism is ongoing. We're observing Andromeda in the process of consuming its neighbors. The halo of old stars in Andromeda is another indicator of past mergers. The old stars in the halo have properties and orbital patterns that suggest they came from destroyed galaxies rather than forming within Andromeda's own disk. Their ages and metallicities, the fraction of elements heavier than hydrogen and helium, are consistent with them having originated from a variety of different galaxies with different star formation and chemical enrichment histories. Let me discuss the observation of Andromeda from different locations on Earth. From the northern hemisphere, Andromeda is best observed in the autumn and winter months when it's highest in the evening sky. It's located in the constellation Andromeda, between the distinctive W shape of Cassiopeia and the Great Square of Pegasus. To find it, stargazers often use these bright stars as guideposts. The key to seeing Andromeda well is to get away from light pollution. From a suburban area with moderate light pollution, Andromeda is visible but appears as a fairly dim, compact patch. From a dark sky location far from cities, Andromeda's appearance is transformed. The galaxy extends far across the sky, much larger than it appears from polluted skies. The central bulge becomes bright and prominent, and the outer disk becomes visible, extending far beyond the central core. The best observations come from high altitude locations with very dark skies. From these locations, binoculars can reveal the structure of Andromeda in detail. Through a small telescope, the galaxy becomes even more impressive. The separation between the bright central bulge and the fainter disk becomes clear. The satellite galaxy M32 appears nearby as a distinct fuzzy blob. Some observers report being able to see dust lanes, regions where dust blocks the light from stars behind it, in telescopic observations. Spectroscopic observations of Andromeda have provided crucial information about its motion, composition, and physical properties. By analyzing the light from different regions of Andromeda, astronomers can determine the velocity of the gas and stars in those regions, revealing the rotation of the galaxy's disk. By analyzing the wavelengths of emission lines from ionized gas, astronomers can determine the temperatures and compositions of the gas. Ultraviolet observations, particularly from space telescopes like the Hubble Space Telescope and the Galaxy Evolution Explorer, have revealed the star-forming regions of Andromeda in detail. Young, hot, massive stars emit copious ultraviolet radiation, so ultraviolet observations show these star-forming regions brightly. Infrared observations have been crucial for understanding the dust content of Andromeda. Dust blocks visible light but emits infrared radiation. By observing Andromeda in infrared light, astronomers can see through the dust and observe stars that would otherwise be hidden. Infrared observations from space telescopes like Spitzer and from ground-based telescopes have revealed the distribution of dust in Andromeda. Radio observations have revealed the distribution of cold gas in Andromeda. Neutral hydrogen atoms emit radio radiation at a characteristic wavelength of 21 centimeters. By observing this emission, astronomers can map the distribution and velocity of the cold gas throughout Andromeda. This has shown that Andromeda has a large reservoir of cold gas that fuels star formation. X-ray observations have revealed energetic processes in Andromeda, binary star systems with black holes or neutron stars, the central supermassive black hole, and hot gas in the galaxy's outer regions. X-ray telescopes like Chandra have provided detailed maps of these X-ray sources. Let me discuss some famous astronomers who have contributed to our understanding of Andromeda. Vesto Melvin Slipher was an American astronomer who, in 1912, discovered that Andromeda is moving toward the Milky Way. Using spectroscopy, analyzing the light from Andromeda to measure its motion, he determined that Andromeda has a blue shift, indicating motion toward us. This was years before Edwin Hubble determined that Andromeda was a separate galaxy. Slipher also made similar spectroscopic observations of many other nebulae, discovering that many of them are moving. Edwin Powell Hubble, as discussed earlier, provided definitive proof that Andromeda is a separate galaxy far beyond the Milky Way. His observations of Cepheid variable stars in Andromeda revolutionized our understanding of the universe. Beyond his work on Andromeda, Hubble went on to discover that the universe itself is expanding, earning him a place among the greatest astronomers in history. Fritz Zwicky was an innovative astronomer who made many discoveries, including the existence of dark matter, inferred from the dynamics of galaxy clusters. He also made observations relevant to Andromeda and proposed theories about galaxy formation. Vera Rubin was a pioneering astronomer who, in the 1970s and 1980s, provided crucial evidence for the existence of dark matter by studying the rotation curves of galaxies, including detailed observations of nearby galaxies like Andromeda. Her work showed that galaxies must contain far more matter than visible stars and gas, dark matter that doesn't emit or absorb light, but whose gravitational effects are detectable. Let me discuss the future of Andromeda observations and what new telescopes will reveal. The James Webb Space Telescope, launched in December 2021, has already begun observing Andromeda. JWST's infrared capabilities allow it to observe individual stars in Andromeda that would be impossible to resolve with previous telescopes. By counting stars in different regions and studying their properties, JWST is providing new insights into Andromeda's structure and star formation history. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will have even greater capabilities than JWST for observing nearby galaxies. It will be able to resolve individual stars across the entirety of Andromeda and will provide an unprecedented census of Andromeda's stellar populations. Ground-based telescopes are also improving. The extremely large telescope under construction in Chile will be one of the largest telescopes ever built when it becomes operational. With its enormous collecting area and advanced adaptive optic systems to correct for atmospheric distortion, it will be able to observe faint structures in Andromeda that are currently invisible. The 30-meter telescope, another extremely large telescope being constructed, will similarly provide unprecedented capabilities for observing Andromeda and other nearby galaxies. These new telescopes will allow astronomers to answer questions about Andromeda that remain mysterious. They'll be able to observe the smallest dwarf satellite galaxies, potentially discovering many more that are currently too faint to detect. They'll be able to map the history of star formation throughout Andromeda in unprecedented detail. They'll be able to study the properties of individual stars and star clusters with unprecedented precision. Let me discuss some of the specific mysteries about Andromeda that remain unsolved. One mystery is the exact mass of Andromeda. While we have good estimates, different measurement techniques give somewhat different results. Some of this uncertainty comes from the difficulty of measuring the distribution of dark matter in the halo. Better understanding of Andromeda's mass distribution will improve our understanding of how the galaxy formed and evolved. Another mystery is the reason for Andromeda's high velocity relative to the Milky Way. It's moving toward us at about 110 kilometers per second, which is faster than its velocity relative to other nearby galaxies. What caused this high velocity? Was Andromeda pulled toward the Milky Way by gravity? Or does Andromeda have a different orbit around the local group's center of mass? These questions are still being investigated. The nature and origin of Andromeda's multiple disk components is another mystery. Evidence suggests there are multiple disks with different properties, possibly at different orientations, but the exact number and properties of these disks remain unclear. Are they the remnants of multiple mergers, or do they represent a single continuous disk that has been warped and distorted by interactions with satellites? The composition and distribution of Andromeda's dark matter is perhaps the deepest mystery. We know dark matter is there because of its gravitational effects, but we don't know what it's made of. Some theories suggest it's composed of weakly interacting massive particles, WIMPs. Others suggest it might be axions or other exotic particles. Direct detection experiments are searching for these particles, but so far they've been unsuccessful. Let me discuss what Andromeda teaches us about the universe and our place in it. Andromeda reminds us that the universe is vast beyond human comprehension. When we look at Andromeda, we're looking at a collection of 1 trillion stars, each potentially surrounded by planets. The distances are so large that light takes 2.5 million years to cross the space between our galaxy and Andromeda. To put this in perspective, when that light left Andromeda, Homo habilis, an ancestor of modern humans, was just beginning to use simple stone tools in Africa. Andromeda also reminds us that the universe is not static. Galaxies move, collide, merge, and transform. Nothing is permanent on cosmic scales. The Andromeda galaxy, as it exists now, will cease to exist as a separate entity in the future. It will merge with the Milky Way and be transformed into a new galaxy. Andromeda is part of the Local Group, a collection of about 80 galaxies that are gravitationally bound to each other. The Local Group is itself part of the Virgo supercluster, which is part of even larger structures. Understanding Andromeda and its relationship to the Milky Way helps us understand the large-scale structure of the universe. Andromeda also provides a laboratory for understanding galaxy formation and evolution. By comparing Andromeda to the Milky Way and other nearby galaxies, astronomers can test theories about how galaxies form, how they grow, and how they evolve. Observations of Andromeda have helped shape our understanding of galaxy formation. Perhaps most importantly, Andromeda represents our connection to the cosmos. When we look at Andromeda, we're observing one of the major structures of the universe. We're recognizing that we're part of something vast and ancient. We're connecting ourselves to the history of the cosmos and to the future of the universe. The future merger of Andromeda and the Milky Way, billions of years from now, will be a cosmic event of tremendous importance. It will reshape both galaxies and create a new merged galaxy. Any civilization that exists billions of years in the future on a planet around one of the stars involved in this merger will observe the sky and witness one of the most dramatic events in the universe, the merger of 2 giant galaxies. Yet from a local perspective, on the scale of individual star systems, the merger might barely be noticed. The distances between stars are so vast that collisions between stars themselves are extraordinarily unlikely. Most stars will pass by each other without close encounters. The solar system might be gently nudged into a new orbit, or it might be dramatically ejected far from the galactic center, or it might remain relatively undisturbed. This contrast between the dramatic large-scale effects of the collision and the minor local effects is one of the most profound lessons that Andromeda teaches us. The universe operates on scales so vast that our daily experience gives us little intuition for them. A collision between galaxies, while violent and cataclysmic on galactic scales, might leave individual star systems largely unaffected. Finally, let me reflect on the philosophical implications of Andromeda. The existence of Andromeda, with its trillion stars and countless planets, raises profound questions about life and consciousness in the universe. Are we alone? Is life common? Is consciousness rare or abundant in the cosmos? These are questions that cannot be answered with our current knowledge, but the mere existence of Andromeda, a galaxy potentially harboring countless worlds, makes the existence of other life seem statistically likely. If life does exist elsewhere in Andromeda, those beings would be observing their own galaxy, wondering about the universe. They would see the Milky Way as we see Andromeda, a distant galaxy of a trillion stars moving slowly through the cosmos. Perhaps they would make the same calculation we have made and recognize that their galaxy is doomed to merge with the Milky Way in the distant future. The light we receive from Andromeda has been traveling for 2.5 million years. In that time, if life exists on planets in Andromeda, that life has evolved, adapted, possibly developed civilizations. Or perhaps life has arisen on new worlds in Andromeda since that light began its journey toward us. Or perhaps life has gone extinct on worlds where it once flourished. We will never know because the light we receive shows us only the past. This is one of the great frustrations and fascinations of astronomy. We can see across vast distances and look back through time, but we can never truly know the present state of distant objects. The universe keeps its secrets, revealing only the past to our telescopes. Andromeda is beautiful. When you look at a photograph of Andromeda, the elegant spiral arms, the dust lanes, the central bulge, you're looking at one of the most beautiful structures in the universe. This beauty emerges from the mathematics of gravity and the physics of galaxies. The spiral structure, the organization of stars and gas, the hierarchy of structures from individual stars to star clusters to the galaxy as a whole, all of this emerges from the simple laws of physics operating over billions of years. There's a deep connection between beauty and truth in physics. The structures that are most beautiful often turn out to be the most profound. Andromeda's beauty reflects its profound nature as a galaxy containing a trillion stars, shaped by billions of years of stellar dynamics and galactic interactions. Let me discuss some remarkable specific observations and discoveries about Andromeda that illustrate the fascination this galaxy holds for astronomers. In 1885, a supernova appeared in Andromeda's bulge and briefly became nearly as bright as the entire galaxy. This supernova, called S Andromedae, was a Type 1a supernova, an explosion of a white dwarf star in a binary system. This observation was crucial to astronomers at the time because it provided additional evidence that Andromeda was a separate galaxy far beyond the Milky Way. If Andromeda were merely a nebula within our own galaxy, a supernova within it shouldn't be nearly as bright as the entire galaxy. Another supernova in Andromeda occurred in 1961, called SN 1961N. This supernova was also a Type 1a explosion and was carefully observed by astronomers. By studying the brightness over time and analyzing the spectrum, astronomers learned more about the properties of Type 1a supernovas. These observations contributed to the eventual realization that Type 1a supernovas could be used as standard candles for measuring cosmic distances. In 1993, another supernova appeared in Andromeda, designated SN 1993J. This was a different type of supernova, a Type 2 supernova, the explosion of a massive star at the end of its life. By observing this supernova, astronomers gathered data about core collapse supernovas and how they evolve over time. The study of supernovas in Andromeda and other nearby galaxies has revealed that supernova rates are not uniform but vary with the properties of the host galaxy. Galaxies with active star formation tend to have higher rates of core collapse, type 2, supernovas. Galaxies with older stellar populations tend to have higher rates of thermonuclear, type 1a supernovas. Andromeda, with its mix of young and old stars, exhibits both types of supernovas. Novae are another class of stellar explosions that occur in Andromeda. Unlike supernovas, which destroy stars, novae are thermonuclear explosions on the surfaces of white dwarf stars in close binary systems. The white dwarf pulls material from a companion star, and when enough material accumulates on the white dwarf's surface, a thermonuclear explosion is triggered. This explosively ejects the accumulated material, after which the process begins again. Astronomers have cataloged hundreds of novae in Andromeda over the past century. By studying the properties of these novae, astronomers learn about the binary star systems in Andromeda and the properties of the white dwarfs and companion stars involved. Let me discuss the specific observational techniques used to study Andromeda and what each technique reveals. Photometry, the measurement of light brightness, is one of the oldest observational techniques used to study Andromeda. By measuring how bright Andromeda appears through filters of different colors, astronomers can determine the colors of regions of the galaxy and infer the properties of the stars in those regions. Blue regions indicate the presence of young, hot, massive stars. Red regions indicate the presence of old, cool stars. Spectroscopy, the analysis of the spectrum of light, provides information about the composition, temperature, and velocity of light-emitting objects. By analyzing the spectrum of light from Andromeda, astronomers can determine the composition of the gas in different regions, the temperature of the gas, and the velocity of the gas and stars as they move through the galaxy. High-resolution imaging with large telescopes or space telescopes allows astronomers to resolve individual stars and star clusters in Andromeda. This has become possible with modern telescopes, whereas older telescopes could only resolve Andromeda as a blur of light. The ability to observe individual stars has revolutionized our understanding of Andromeda, allowing astronomers to determine the ages and compositions of stars in different regions. Astrometry, the measurement of positions of stars, has revealed the motion of stars within Andromeda. By measuring the positions of stars at different times, astronomers can determine how fast stars are moving and in what directions. This reveals the rotation of Andromeda's disk and the dynamics of the galaxy as a whole. Photometric redshift measurements provide information about distances to objects within Andromeda. By measuring the color of light from an object and comparing it to predictions from stellar models, astronomers can estimate the distance to that object. This technique has been used to measure distances to star clusters and to the faint outer regions of Andromeda. Gravitational lensing, bending of light by the gravity of massive objects, has been observed in Andromeda and provides information about the distribution of dark matter. When light from a distant object passes near Andromeda, Andromeda's gravity bends the light path. By studying how light is bent, astronomers can map the distribution of dark matter in Andromeda. Let me discuss the chemical composition and metallicity of Andromeda in detail. Metallicity in astronomy refers to the abundance of elements heavier than hydrogen and helium. Iron, oxygen, carbon, nitrogen, and other heavy elements are all considered metals by astronomers. The metallicity of a region of Andromeda tells us about the history of star formation in that region. Young stars forming in Andromeda have higher metallicity than old stars because they've had access to material enriched by the nucleosynthesis of previous generations of stars. Each generation of stars creates heavier elements and spreads them into the interstellar medium when the stars explode as supernovas. The next generation of stars forms from this enriched material and has higher metallicity. By measuring the metallicity of stars and gas throughout Andromeda, astronomers can reconstruct the history of star formation and chemical enrichment. Stars in Andromeda's disk tend to have higher metallicity than stars in the halo. This makes sense because disk stars formed relatively recently from material that had been enriched by many previous generations of stars. Halo stars formed long ago before much chemical enrichment had occurred, and so they have lower metallicity. The metallicity gradient within Andromeda, the systematic change in metallicity from the center to the outer regions, provides information about how Andromeda has grown. If Andromeda grew through the merger of smaller galaxies, then the chemical properties of the merged galaxies might be visible in the metallicity patterns observed today. Let me discuss the future fate of Andromeda in cosmic context. In about 4.5 billion years, as I've discussed, Andromeda will collide with the Milky Way. But this isn't the end of Andromeda's story. Even after merging with the Milky Way, the combined galaxy will continue to evolve. Other nearby galaxies might eventually merge with the combined galaxy. The local group might undergo reorganization as the gravitational hierarchy of the group evolves. Over even longer timescales, trillions of years, the fate of Andromeda and all galaxies becomes tied to the fate of the universe itself. If the universe continues to expand forever, galaxies will gradually grow colder and dimmer as the stars within them exhaust their fuel. Stars will go out one by one. Black holes will eventually evaporate through Hawking radiation. Protons might decay. Eventually, the universe will reach a state of maximum entropy, a dark, cold, dead universe with no structure or complexity. This is the ultimate fate not just of Andromeda, but of all galaxies and all stars. Over timescales so vast that they're almost incomprehensible, everything will be gone. But this needn't be depressing. Right now, in this cosmic moment, Andromeda exists in all its glory. It's a magnificent structure containing 1 trillion stars, potentially harboring countless worlds. The fact that it won't last forever doesn't diminish its present beauty and significance. Let me discuss how Andromeda is used in education and public outreach. Andromeda is perhaps the most famous galaxy besides our own Milky Way. It appears in countless textbooks, popular science books, and documentaries. Its distant, alien appearance captures the imagination. The idea that this galaxy is moving toward ours, that billions of years in the future the two will merge into a single galaxy, is genuinely exciting and makes Andromeda a powerful teaching tool. Andromeda's visibility to the naked eye is particularly valuable for education. Teachers can take students to a dark location and point out Andromeda in the night sky. Students can see for themselves that this object really exists, that they're actually looking at a distant galaxy. This direct observation creates a visceral connection to the cosmos that abstract discussions of galaxy distances and sizes cannot match. Planetariums often feature shows about Andromeda,
using three-dimensional visualizations to convey the scale and structure of the galaxy. These visualizations can show viewers flying through Andromeda, seeing the
Structure from different angles, appreciating the scale of the trillion stars. Simulations of the collision between Andromeda and the Milky Way are also valuable educational tools. Visualizations of the merger process help viewers understand galaxy dynamics, the effects of gravity on large scales, and the vast timescales of cosmic processes. Andromeda is also used in discussions of astrobiology and the search for extraterrestrial life. The trillion stars in Andromeda suggest countless planets, many of which could potentially harbor life. These discussions broaden people's perspective on humanity's place in the universe and can inspire interest in science and exploration. Let me discuss some common misconceptions about Andromeda. One common misconception is that Andromeda is so far away that light from it has been traveling for billions of years. In fact, the light has been traveling for 2.5 million years, not billions. While this is a vast amount of time by human standards, it's much shorter than the age of the universe, about 13.8 billion years, or even the age of Earth, about 4.5 billion years. Another misconception is that when we observe Andromeda, we're seeing it as it is now. In reality, we're seeing it as it was 2.5 million years ago. Andromeda has changed significantly in that time. Stars have been born and died, supernovas have occurred, the structure has been subtly altered, but we have no way of knowing what Andromeda looks like at this very moment. A third misconception is that when Andromeda and the Milky Way collide, stars will smash together dramatically. In reality, due to the vast distances between stars, direct collisions between stars are extraordinarily unlikely. The galaxies will merge through gravitational interactions, but individual stars will rarely come close to each other. Another misconception is that Andromeda will soon collide with the Milky Way, and we need to worry about it. In reality, the collision won't occur for another 4.5 billion years. At the current rate of human technological progress, it's impossible to predict what civilization will be like in 4.5 billion years, or whether humans will even exist. This isn't a practical concern for current civilization. Let me discuss the role of Andromeda in our understanding of dark matter. Observations of Andromeda's rotation curve, how fast different parts of the galaxy rotate, provided evidence for the existence of dark matter. The rotation curve of a galaxy shows the orbital velocity of objects at different distances from the galactic center. For a galaxy made only of visible matter, the rotation curve should fall off at large distances from the center. Objects at larger distances should orbit more slowly. In reality, for Andromeda and other galaxies, the rotation curve remains flat or nearly flat even at large distances from the center. This is only possible if there's far more mass in the galaxy than visible stars and gas can account for. This extra mass is dark matter, matter that we can infer exists from its gravitational effects, but which we cannot directly see. Andromeda's dark matter halo is probably much more massive than the visible galaxy. The visible stars and gas make up only a small fraction of the total mass of Andromeda. The rest is dark matter distributed in a spherical halo surrounding the galaxy. The nature of this dark matter remains mysterious. Is it composed of ordinary matter, atoms, neutrons, electrons, that simply doesn't emit, absorb, or reflect light? Or is it composed of exotic particles that we haven't yet discovered? Experiments searching for dark matter particles continue, but so far none have been detected. Understanding dark matter is crucial for understanding Andromeda and galaxy formation in general. The distribution of dark matter affects how galaxies form and evolve. It affects the gravitational dynamics of galaxy collisions and mergers. Let me discuss what Andromeda means for our understanding of habitability and life in the universe. Andromeda contains approximately 1 trillion stars. If even a tiny fraction of these stars have planets, there could be billions or trillions of planets in Andromeda. If planets form with the same frequency around stars in Andromeda as they do around stars in the Milky Way, then the number of potentially habitable planets in Andromeda is astronomical. The Drake equation, proposed in 1961 by Frank Drake, is a way of thinking about the number of communicative civilizations in the galaxy. The equation multiplies together the estimated values of various factors: the rate of star formation, the fraction of stars with planets, the fraction of planets that are habitable, the fraction of habitable planets that develop life, the fraction of life-bearing planets that develop intelligent life, the fraction of intelligent civilizations that communicate, and the average lifespan of communicative civilizations. While the Drake equation is speculative, we don't know the actual values of most of these factors. It illustrates how the existence of countless planets in Andromeda suggests the possibility of life. Even if life is incredibly rare, developing only on 1 in a billion planets, Andromeda would still have millions of life-bearing worlds. If intelligent civilization is even rarer, developing on only 1 in a trillion planets with life, Andromeda would still potentially have millions of civilizations. Of course, this is all speculation. We have no direct evidence of life beyond Earth. But the enormity of Andromeda, a galaxy with 1 trillion stars, makes it statistically likely that life, if it's possible through chemistry and physics, would arise somewhere in Andromeda. Let me discuss the observational challenges in studying Andromeda and how these challenges have driven technological advances. One major challenge is that Andromeda is so large and extended that it's difficult to observe entirely. Ground-based telescopes have limited fields of view and can only see a portion of Andromeda at a time. Space telescopes have smaller fields of view, but aren't limited by atmospheric distortion. Observing Andromeda in its entirety requires combining observations from multiple telescopes and multiple passes. The faintness of Andromeda's outer regions is another challenge. As we look at increasingly distant parts of Andromeda, the light becomes fainter and fainter. It's extraordinarily challenging to detect faint light, requiring large telescopes with sensitive detectors and long exposure times. The problem of dust extinction is another challenge. Dust within Andromeda blocks visible light, making it difficult to observe objects hidden behind the dust. However, infrared light penetrates through dust, so infrared observations can reveal objects that are invisible in visible light. These observational challenges have driven the development of new technologies. More sensitive detectors have been developed. Larger telescopes have been built. Space telescopes with no atmospheric interference have been launched. These technological advances, driven partly by the desire to better understand Andromeda and other galaxies, have had applications far beyond astronomy. Let me make final philosophical reflections on what Andromeda means to human consciousness and our understanding of existence. When you look at Andromeda, whether with naked eyes, binoculars, a telescope, or in a photograph, you're connecting yourself across an immense distance to a distant galaxy. You're observing something that exists independently of your observation, that would continue to exist even if no humans existed to observe it. This is humbling. Andromeda is beautiful. Its elegant spiral structure, its trillion stars arranged in cosmic patterns, its vast halo of dark matter extending far into space. All of this is genuinely beautiful. This beauty suggests that the universe has an order, a structure, an aesthetic quality that transcends human preferences and expectations. Andromeda connects us to the deep past. The light you see from Andromeda has been traveling through space for longer than recorded human history. It carries information about a distant galaxy from an era when humans were just beginning to develop culture and civilization. Andromeda also connects us to the distant future. We know that 4.5 billion years in the future, Andromeda will collide with our galaxy and fundamentally transform both, some being perhaps human descendants, perhaps some other species, perhaps something we can't yet imagine, might witness this cosmic collision. They will look up at a sky transformed by the merger of two galaxies. Andromeda reminds us that we live in a universe far larger, older, and more complex than our everyday experience suggests. This perspective, gained by studying objects like Andromeda, can be transformative. It can inspire wonder and awe. It can expand our sense of what's possible. It can help us recognize our connection to the cosmos. Andromeda is a message from the universe. It tells us about the scale of reality. It tells us about the processes of galaxy formation and evolution. It tells us about dark matter and mysterious forces we don't fully understand. It tells us about the beauty and elegance of natural structures shaped by physics and gravity over billions of years. The study of Andromeda is one of humanity's great scientific achievements. Through careful observation, clever reasoning, and technological innovation, we've learned to decode the light from a distant galaxy and extract vast amounts of information about it. This is a testament to human curiosity and ingenuity. Let me discuss specific stellar populations in Andromeda and what they reveal. Andromeda's disk contains predominantly young blue stars. These stars are hot, massive, and short-lived. A massive star might live for only a few million years before exhausting its fuel and exploding as a supernova. The presence of these young stars indicates that star formation is actively occurring in Andromeda's disk right now. The spiral arms of Andromeda are particularly rich in young stars. This makes sense because the spiral arms are regions where gas is compressed and where conditions are favorable for star formation. As gas clouds in the disk pass through the spiral arms, the compression triggers the gravitational collapse that leads to new star formation. By counting the young stars in different regions of Andromeda and measuring their ages, astronomers can map the history of star formation throughout Andromeda. Some regions have been forming stars continuously for billions of years. Other regions have undergone bursts of star formation at particular times in the past. Andromeda's central bulge, in contrast, contains predominantly old, red stars. These are stars that formed billions of years ago and have slowly cooled and dimmed as they've aged. The oldest stars in Andromeda's bulge are approximately 13 billion years old, nearly as old as the universe itself. The globular clusters orbiting in Andromeda's halo are even older. These ancient collections of hundreds of thousands of stars contain some of the oldest stars known. By measuring the ages of stars in globular clusters, astronomers can estimate when Andromeda's halo formed, early in the history of the universe, probably within the first billion years after the Big Bang. The contrast between the young stars in the disk and the old stars in the bulge and halo tells a story about Andromeda's evolution. The galaxy formed early in cosmic history. The halo formed first. Later, a disk of young stars formed and has been continuously regenerated by new star formation over billions of years. Let me discuss the gas content of Andromeda in detail. Andromeda contains vast reservoirs of gas, both ionized gas, plasma, and neutral hydrogen gas. This gas is essential for star formation. New stars form when gas clouds collapse under gravity, compress, heat up, and eventually reach temperatures high enough for nuclear fusion to begin. The gas in Andromeda is not distributed uniformly. Gas is concentrated in the disk, particularly in the spiral arms. The central regions of Andromeda, particularly the central bulge, have relatively little gas. The halo has minimal gas. The interstellar medium, the gas and dust between stars, in Andromeda's disk has a complex structure. There are giant molecular clouds, massive clouds of molecular hydrogen gas mixed with dust particles. These clouds are the sites where new stars form. There are also smaller clouds, more diffuse gas, and shock waves where gas collides and heats up. Supernovas heat the interstellar medium. When a star explodes as a supernova, it releases tremendous energy, creating a shock wave that heats the surrounding gas. This hot gas expands and can trigger additional star formation in some cases, or can suppress star formation in other cases by blowing away the gas that would otherwise form new stars. The composition of Andromeda's gas reveals its chemical enrichment history. The gas is enriched with heavier elements produced by previous generations of stars. Regions with higher star formation rates tend to have more enriched gas because more previous supernovas have occurred to enrich the gas with heavy elements. Let me discuss binary and multiple star systems in Andromeda. A significant fraction of stars exist in binary systems, pairs of stars orbiting each other around their common center of mass. Some of these binary systems contain interactions between the stars that are visible from Earth. Some binary systems in Andromeda are contact binaries, pairs of stars so close that they're distorted by each other's gravity and may actually touch. Material can flow from one star to the other, creating complex dynamics and sometimes spectacular emissions. Some binary systems in Andromeda are X-ray binaries, systems containing a neutron star or black hole that pulls material from a companion star. As material falls toward the neutron star or black hole, it heats up to millions of degrees and emits X-rays. These systems are among the brightest X-ray sources in Andromeda. Eclipsing binary systems in Andromeda provide valuable opportunities for precise measurements. When one star passes in front of the other, from our perspective, the total light from the system decreases. By measuring the dip in brightness and analyzing the eclipse, astronomers can determine the radii and masses of the stars in the system. By studying binary systems in Andromeda, astronomers learn about stellar evolution, stellar masses and sizes, and the interactions between stars. This knowledge contributes to our general understanding of how stars work. Let me discuss the specific discovery and naming of Andromeda. The name Andromeda comes from the constellation in which the galaxy is located. The constellation Andromeda is named for a character in Greek mythology, the daughter of King Cepheus and Queen Cassiopeia of Ethiopia. In the mythology, Andromeda was chained to a rock and rescued by Perseus. The name Andromeda Galaxy, or Andromeda Nebula, before it was known to be a separate galaxy, has been used for centuries. But in modern astronomy, the galaxy is often referred to by its Messier catalog number, M31, assigned by Charles Messier in 1764 when he was cataloging nebulae visible to the naked eye. The recognition of Andromeda as a separate galaxy came gradually, not as a single sudden revelation. Speculation about the nature of nebulae had been ongoing for centuries. Observations with better and better telescopes revealed more structure in Andromeda, suggesting it might be a separate world of stars. But not until Edwin Hubble's observations of Cepheid variables in 1924 to 1925 was definitive proof provided. The discovery of Andromeda as a separate galaxy was revolutionary. It fundamentally changed humanity's understanding of the universe. Before this discovery, the universe was thought to be small, containing only the Milky Way and its constituent stars and nebulae. After this discovery, the universe suddenly became vastly larger, with billions of other galaxies beyond our own. Let me discuss the role of Andromeda in cosmology and large-scale structure. Andromeda and the Milky Way are both massive spiral galaxies in the local group. The local group is a small cluster of approximately 80 galaxies bound together by gravity. The Milky Way and Andromeda are the two most massive members of the local group and dominate its dynamics. The local group itself is part of the Virgo supercluster, a much larger structure containing tens of thousands of galaxies. The Virgo supercluster is centered on the Virgo cluster, a massive cluster of galaxies about 65 million light years away. The Milky Way and Andromeda are being pulled toward the Virgo cluster by its gravitational attraction. This motion contributes to the observed motion of Andromeda toward the Milky Way. Part of Andromeda's motion is due to being pulled toward the Virgo cluster along with the Milky Way. Understanding Andromeda's place in the large-scale structure of the universe contributes to our understanding of how the universe is organized. Galaxies are not distributed uniformly throughout space. Instead, they're organized into clusters and superclusters with large empty voids between the structures. This cosmic web structure is a fundamental aspect of the universe. Let me discuss some of the specific challenges faced by Andromeda that don't occur for the Milky Way. Observing Andromeda face-on, seeing its full disk and structure, is different from observing the Milky Way, where we're embedded within the disk. Astronomers are inside the Milky Way looking out, which makes the structure harder to determine. But we can observe Andromeda face-on from outside, seeing the full structure directly. This gives us a direct view of what a spiral galaxy looks like that we can't get for our own galaxy. Andromeda's orientation relative to us has been beneficial for studying its structure. If Andromeda were oriented edge-on, we'd see just a thin line, making structure harder to discern. If it were at some intermediate angle, its structure would be partially obscured. But Andromeda is tilted at an angle that allows us to see much of its structure directly. Tidal effects on Andromeda's satellite galaxies are more dramatic than tidal effects on the Milky Way satellites. Andromeda's satellite galaxies are being disrupted and consumed more rapidly than the Milky Way's satellites. The Sagittarius dwarf elliptical galaxy is currently being torn apart by the Milky Way, but this process seems to be less advanced than similar processes occurring to some of Andromeda's satellites. Let me discuss the evolution of Andromeda observation technology over the past century. In the early 1900s, when Andromeda was first being observed in detail, photographic plates were the primary recording medium. Astronomers would expose plates for hours at a time, building up an image of Andromeda. These photographs were of relatively low quality by modern standards, grainy and low contrast. Spectroscopic observations in this era used spectrographs attached to telescopes. These instruments would split the light from Andromeda into its constituent wavelengths, creating a spectrum that could be analyzed to determine the composition, temperature, and motion of the light source. By the mid-20th century, photoelectric detectors began to replace photographic plates. These detectors were much more sensitive and allowed for more precise measurements. Charge coupled devices, CCDs, invented in the 1970s, revolutionized observational astronomy by providing digital imaging with unprecedented sensitivity. The advent of space telescopes like Hubble opened new possibilities for observing Andromeda without atmospheric distortion. Hubble's observations of individual stars in Andromeda have been invaluable for understanding the galaxy's stellar populations. Modern digital cameras and detectors allow for real time or near real time observations. Adaptive optic systems on ground based telescopes use deformable mirrors to correct for atmospheric distortion, allowing ground based telescopes to achieve resolutions approaching those of space telescopes. These technological advances have transformed our understanding of Andromeda. Each new technology has revealed new details and answered new questions while also raising new mysteries. Let me discuss some of the personal experiences and perspectives of astronomers who study Andromeda. Many professional astronomers describe a profound emotional response to Andromeda. Looking at Andromeda, whether through a telescope or in a photograph, can inspire awe and wonder. Understanding that you're looking at a galaxy containing 1 trillion stars, each potentially surrounded by planets, is humbling. Amateur astronomers also find Andromeda compelling. Many amateur astronomers make their first telescopic observation of Andromeda. The ability to see a distant galaxy with your own eyes, to know that what you're looking at is real, that it exists independently of your observation, is a transformative experience for many people. Some astronomers have dedicated their careers to studying Andromeda. They've spent decades observing the galaxy, building up understanding of its structure and evolution. The intimacy with a particular subject matter that comes from focused study creates a personal connection that casual observers might not experience. Scientific conferences on topics like galaxy structure often feature sessions on Andromeda. Researchers present their latest findings about Andromeda's satellites, its dark matter distribution, its star formation history, and other aspects. These presentations represent the cutting edge of our understanding of the galaxy. Let me discuss what remaining mysteries about Andromeda captivate astronomers today. The detailed history of Andromeda's mergers remains partially mysterious. We can identify evidence of past mergers in the streams and shells of stars in the halo, but determining exactly when these mergers occurred and the properties of the galaxies involved requires detailed analysis and modeling that's still ongoing. The dynamics of Andromeda's spiral arms continue to fascinate astronomers. How are the spiral arms maintained? Why do they have their particular shape? How do they interact with the surrounding disk and halo? These questions are still being investigated through both observations and theoretical modeling. The properties and origin of Andromeda's satellite galaxies raise interesting questions. How did these galaxies form? Why is there such a wide range of sizes and properties among the satellites? What determines whether a satellite survives or is completely disrupted? The ultimate fate of Andromeda beyond its merger with the Milky Way is another mystery. After the merger is complete, what will the resulting galaxy do? Will it merge with other nearby galaxies? Will it enter a quiescent phase of slow evolution? These questions about the far future are speculative, but they're worth pondering. Let me make final thoughts on why Andromeda matters. Andromeda matters scientifically because it teaches us how galaxies work. By comparing Andromeda to the Milky Way and other galaxies, we learn about galaxy structure, galaxy evolution, the role of dark matter, and the processes that shape galaxies. Andromeda matters historically because it revealed to humanity that the universe is vastly larger than previously imagined. The discovery that Andromeda is a separate galaxy, far beyond our own, was one of the most profound scientific discoveries in human history. Andromeda matters culturally because it's beautiful and inspires wonder. Throughout human history, humans have looked up at the night sky with awe and curiosity. Andromeda, visible to the naked eye as a faint fuzzy patch yet representing a trillion-star galaxy, embodies that sense of wonder and mystery. Andromeda matters philosophically because it reminds us of our place in the universe. We are not at the center of anything. We're inhabitants of a small planet orbiting an ordinary star in one galaxy among billions. This perspective can be humbling and can inspire us to think beyond our immediate concerns to larger questions about existence and meaning. Andromeda will matter in the future as well. In billions of years, when our galaxy merges with Andromeda, the event will create a new galaxy and reshape the cosmos as far as local space is concerned. The descendants of any beings living in this region of space at that time will look up at a transformed night sky and will remember or study in their history the time when two great galaxies became one. Let me discuss some specific astronomical phenomena observed in and around Andromeda. Planetary nebulae in Andromeda are among the most fascinating objects. A planetary nebula is created when a star like the Sun reaches the end of its life, sheds its outer layers, and creates a glowing shell of gas. These objects are small and intricate, with delicate structures created by the outflow of gas from the dying star. Hundreds of planetary nebulae have been identified in Andromeda, and they're subjects of continuing study. Emission nebulae in Andromeda appear as bright regions of ionized gas, gas where atoms have been stripped of electrons. This ionization is usually caused by ultraviolet radiation from nearby hot young stars. The ionized gas glows by emitting photons at specific wavelengths, creating colorful nebulae that are spectacular in photographs. Reflection nebulae in Andromeda are clouds of dust that don't emit their own light, but instead reflect light from nearby stars. These nebulae appear bluish because dust particles preferentially reflect blue light, just as Earth's atmosphere appears blue because of Rayleigh's scattering of blue light. Dark nebulae are clouds of gas and dust so dense that they block all light from stars behind them, appearing as dark regions against the background. Some of the most dramatic dark nebulae in Andromeda create the dust lanes that are visible in photographs of the galaxy. Supernova remnants, the expanding shells of gas left behind by stellar explosions, continue to shine for thousands of years after the supernova event. Several supernova remnants from ancient supernovas in Andromeda have been cataloged. These remnants show up particularly well in X-ray observations because the expanding gas is heated to very high temperatures. Let me discuss the role of cosmic rays and radiation in Andromeda. Cosmic rays are high-energy particles that constantly bombard the galaxy. They originate from various sources, some from the Sun, some from distant supernovas, some from the galactic center. Cosmic rays have effects throughout the galaxy, ionizing atoms, heating gas, and creating secondary particle cascades. The radiation environment in Andromeda affects planetary atmospheres and the potential for life. Planets with strong magnetic fields and thick atmospheres can shield their surfaces from radiation. But planets without adequate protection would be subject to intense radiation and would be less favorable for life as we understand it. Observing cosmic rays from Andromeda is challenging because most cosmic rays are electrically charged and are deflected by magnetic fields. We can't easily determine where a cosmic ray originated just by observing where it arrives. However, high energy photons from Andromeda, which are unaffected by magnetic fields, can provide information about cosmic ray acceleration in the galaxy. Let me discuss some specific star clusters in Andromeda that have been studied in detail. M31. G is a luminous star cluster in Andromeda that has been extensively studied. It contains thousands of stars and displays a rich variety of stellar types and ages. By studying the properties of individual stars in M31G, astronomers learn about stellar evolution and the processes that govern star formation in clusters. Many globular clusters in Andromeda's
Halo have been cataloged and studied. These ancient, dense star clusters contain hundreds of thousands of stars in a region only a few tens of light years across. The central regions of globular clusters have such high stellar density that stellar collisions might occasionally occur. By studying globular clusters in Andromeda, astronomers can determine their ages, which helps establish when Andromeda's halo formed. The oldest globular clusters are nearly as old as the universe, suggesting that Andromeda's halo formed very early in cosmic history. Let me discuss the specific role of supernovae in enriching Andromeda with heavy elements. Supernovae are crucial to galaxy chemical evolution. When a star explodes as a supernova, it ejects the material it created through nucleosynthesis into the interstellar medium. For Type II supernova, explosions of massive stars, the ejected material includes iron, nickel, oxygen, and other elements created in the star's core. For Type I, a supernova A, thermonuclear explosions of white dwarfs, the ejected material includes iron peak elements. This enriched material mixes with the interstellar medium and is incorporated into new gas clouds. When new stars form from these enriched clouds, they contain higher abundances of heavy elements than the stars that came before them. By measuring the abundances of heavy elements in stars and gas throughout Andromeda, astronomers can trace the history of supernova activity and star formation. Regions where supernova have been particularly active show higher abundances of heavy elements. The rate of supernova activity in Andromeda has varied over cosmic time. Early in Andromeda's history, when star formation was more intense, the supernova rate was probably higher. More recently, as the star formation rate has declined, the supernova rate has also declined. Let me discuss some current questions about Andromeda that are driving ongoing research. One question concerns the specific nature of Andromeda's dark matter halo. Is it distributed smoothly, or does it contain substructure? How does the distribution of dark matter affect Andromeda's galaxy dynamics? Current observations and theoretical models are still refining our understanding. Another question concerns the detailed merger history of Andromeda. We can see evidence of past mergers, but determining exactly when each merger occurred and the properties of the galaxies involved requires detailed analysis. Different lines of evidence, stellar streams, metallicity gradients, disk components, can provide complementary information about the merger history. A third question concerns the origin of Andromeda's satellite galaxies. Are they primordial, formed with Andromeda early in cosmic history, or did they form more recently? Are there as many satellites as we expect based on galaxy formation simulations, or are there fewer than expected? A puzzle sometimes called the missing satellites problem. A fourth question concerns the dynamics of the impending collision with the Milky Way. We can simulate what will happen based on our current understanding, but
These simulations depend on assumptions about the initial conditions and galaxy properties. As we learn more about the Milky Way and Andromeda, our simulations can become more accurate. Let me discuss how Andromeda has been represented in popular culture. Andromeda has been featured in numerous science fiction novels, films, and television shows. The idea of a collision between two galaxies is dramatic and has been used as a plot device in various works of fiction. Sometimes the collision is portrayed as catastrophic and imminent. Other times it's used as a philosophical framing device for thinking about cosmic scales and humanity's place in the universe. The name Andromeda has been used for starships in various science fiction properties, reflecting the galaxy's significance as a distant, exotic location in human imagination. Andromeda's visibility to the naked eye has made it a touchstone for people thinking about the cosmos. Throughout human history, people have looked at Andromeda and wondered what it is and what might lie within it. This wondering has contributed to the development of astronomy and to human curiosity about the universe. Let me discuss the technological requirements for different observations of Andromeda. Naked eye observation of Andromeda requires only dark skies and the ability to recognize the fuzzy patch in the constellation Andromeda. No equipment is needed, making this observation accessible to anyone. Binocular observation reveals more structure. The disk and bulge become more distinct, and satellites like M32 become visible. Good binoculars, at least 10 times 50 from a dark location, are recommended. Telescopic observation reveals even more detail. A small telescope, 4-inch or larger aperture, can show the structure of Andromeda's disk and reveals star clusters and other features. Larger telescopes reveal fainter structures and allow observation of individual stars in some regions. Spectroscopic observation requires telescopes equipped with spectrographs and sensitive detectors. Spectrographs split light into its constituent wavelengths, allowing detailed analysis of the composition, temperature, and motion of light sources in Andromeda. Photographic observation requires cameras, digital or film, attached to telescopes. Long exposure photographs reveal fainter structures and allow detailed mapping of Andromeda's extent and structure. Space-based observation eliminates atmospheric distortion and allows observation of wavelengths blocked by Earth's atmosphere. Space telescopes like Hubble have provided unprecedented views of Andromeda's structure and allow observation of very faint objects that would be impossible to detect from Earth. Let me discuss why Andromeda remains relevant to 21st century astronomy. Even with all the sophisticated telescopes and instruments available, Andromeda retains mysteries and continues to be the subject of active research. New telescopes being built and launched will provide new perspectives on Andromeda and answer questions that current telescopes cannot address. Andromeda is a nearby laboratory for understanding galaxy physics. The processes that operate in Andromeda, star formation, supernova explosions, black hole dynamics, dark matter distribution, all operate similarly in distant galaxies. By understanding Andromeda in detail, astronomers build a foundation for understanding all galaxies. Andromeda also serves as a test case for theoretical models of galaxy formation and evolution. Computer simulations that model galaxy formation can be compared with observations of Andromeda to test whether the simulations match reality. When simulations don't match observations, scientists revise the models or the parameters, improving their understanding. In conclusion, Andromeda is an extraordinary object worthy of lifelong study. It's large enough to contain 1 trillion stars, yet close enough to observe in detail. It's similar enough to our Milky Way that understanding it helps us understand our own galaxy, yet different enough that each comparison reveals something new. It's beautiful to look at, profound to contemplate, and continues to inspire scientists and citizens alike to think about the cosmos and humanity's place within it. Let me make one final discussion about the implications of Andromeda's upcoming collision for the long term future of the universe. When Andromeda collides with the Milky Way in approximately 4.5 billion years, the result will be a new galaxy. Let's call it the Andromeda Way or Milkomeda. This new galaxy will be larger than either parent galaxy, with perhaps 4 to 5 trillion stars combined. But this merger is not an isolated event in cosmic history. It's one incident in an ongoing process of cosmic reorganization. Over the history of the universe, galaxies have been continuously colliding, merging, and evolving. The universe is not static, it's a dynamic system undergoing constant change. The ultimate fate of the Andromeda Way galaxy depends on the fate of the universe as a whole. If the universe continues to expand forever, which current cosmological evidence suggests it will, then the Andromeda Way will gradually become isolated. Its stars will gradually exhaust their fuel. The galaxy will grow colder and dimmer over immense timescales. Eventually, over timescales of 10 to the power of 100 years or longer. The Google years, far longer than the current age of the universe. Even protons might decay, destroying the very matter from which stars and planets are made. Black holes might be the last massive objects remaining, slowly evaporating through Hawking radiation over timescales of 10 to the power of 67 years. But this ultimate fate is so distant in the future, so incomprehensibly far away, that it's beyond meaningful contemplation. For all practical purposes, the Andromeda Way that forms from the collision of Andromeda and the Milky Way will persist for essentially forever on human timescales. What will the Andromeda Way be like after the merger is complete? Astronomers can use simulations to make predictions, but many details remain uncertain. The final galaxy will probably be elliptical rather than spiral in shape. It will contain stars with a wide range of ages and properties, from young stars recently formed from merging gas to ancient stars that were born billions of years ago. The supermassive black hole at the center of the merged galaxy will be about 4.1 billion times the mass of the Sun. The sum of Andromeda's black hole, 140 million solar masses, and the Milky Way's black hole, about 4 million solar masses. This immense black hole will dominate the central region of the merged galaxy, with millions of stars orbiting it at tremendous velocities. The halo of the merged galaxy will contain streams and shells of stars, evidence of the merger, for billions of years. These structures will gradually disperse as the newly merged galaxy evolves and reaches equilibrium. Let me discuss how the merger will be perceived by intelligent observers who might exist at that time. If any intelligent civilizations survive and observe the galaxy during the merger, they will witness one of the most spectacular cosmic events possible, the merger of two galaxies. The night sky will be transformed by this event. Stars will be thrown into new orbits. The overall shape of the galaxy will change as the merger progresses. For civilizations in stable regions that don't get disrupted during the merger, the event might be more of a spectacle than a catastrophe. Their night sky will change over millions of years as the shape of the galaxy transforms. But they might continue to exist and observe this cosmic drama unfold. for civilizations in regions that do get disrupted, for instance, regions near the centers of the merging black holes or near the dense centers of the galactic bulges, the effects could be more severe. Stars could be ejected from the galaxy entirely. Planets could be scattered from their original orbits. Life might not survive in these regions. But as I've emphasized before, the probability of any individual star system actually being destroyed in the collision is extremely small. Most star systems will be nudged or deflected, but will survive the collision intact. Let me discuss how understanding Andromeda connects to other fields of astronomy and science. The study of Andromeda connects to extragalactic astronomy, the study of objects beyond the Milky Way. By understanding Andromeda, we understand the processes that operate in all galaxies. This knowledge helps us interpret observations of distant, faint galaxies that we can barely resolve into individual stars. The study of Andromeda connects to cosmology, the study of the universe as a whole. The position and motion of Andromeda relative to the Milky Way provides information about the large-scale structure and expansion of the universe. The study of Andromeda connects to astrobiology, the study of life in the universe. The presence of 1 trillion potentially habitable worlds in Andromeda raises profound questions about the origin of life and its prevalence in the cosmos. The study of Andromeda connects to physics itself. The physics that governs galaxy formation, galaxy dynamics, and the evolution of stars applies not just in Andromeda, but throughout the universe. By studying Andromeda, we test and refine our understanding of physics. The study of Andromeda also connects to philosophy and the history of ideas. The recognition that Andromeda is a separate galaxy far beyond our own was a watershed moment in human intellectual history. It fundamentally changed how we understand our place in the universe. Finally, let me address the question, why should you care about Andromeda? You should care about Andromeda because it represents one of humanity's great achievements, our ability to understand the universe through observation and reason. Andromeda is visible without a telescope, yet understanding what it is and where it is required centuries of careful observation and brilliant reasoning. That achievement should inspire you. You should care about Andromeda because it connects you to something vast and eternal. When you look at Andromeda, you're connecting across 2.5 million light-years of space to observe a galaxy containing 1 trillion stars. You're participating in a tradition of human observation and wonder that goes back centuries. You're contributing to the chain of observers who have looked at Andromeda throughout history and wondered about it. You should care about Andromeda because it provides perspective. The problems you face in your daily life, as important as they might seem, occur against the backdrop of a universe far grander than those problems. This perspective can be comforting. It can help you see past immediate concerns to bigger questions and larger purposes. You should care about Andromeda because it's beautiful. The simple appreciation of beauty, the aesthetic experience of seeing something magnificent and well-crafted, is a valid reason for interest in itself. Andromeda, with its elegant spiral arms and its 1 trillion stars, is objectively beautiful. You should care about Andromeda because it's our neighbor. In the coming billions of years, our galaxy will merge with Andromeda. This will be a transformative event for our galaxy and for any intelligent observers present at the time. Understanding Andromeda and its properties is understanding something that will deeply affect our cosmic future, however distant that future might be. Let me discuss one final important aspect: how observations of Andromeda have shaped cosmological models.
when astronomers observed that Andromeda is moving toward the Milky Way at a velocity of about 110 kilometers per second, this raised a question. What is the overall structure of motion in the local universe? Are all nearby galaxies simply moving toward each other randomly, or is there some pattern to these motions? Investigation of these motions revealed that the Milky Way and Andromeda are both being gravitationally attracted toward the Virgo cluster, a massive cluster of galaxies about 65 million light-years away. The gravitational pull of the Virgo cluster affects the motion of nearby galaxies, pulling them toward it. This discovery contributed to our understanding of large-scale structure in the universe. Galaxies are not distributed uniformly. They're concentrated in clusters, which are themselves organized into superclusters. The local group containing the Milky Way, Andromeda, and about 80 other galaxies is being attracted toward the Virgo cluster, which is the center of gravity in our local region of space. This understanding has implications for cosmology. If the universe is distributed in this lumpy, hierarchical way, with galaxies concentrated in clusters and voids between clusters, this affects how we model the large-scale evolution of the universe and how we calculate the overall density of matter and energy. Observations of Andromeda have also contributed to our understanding of the Hubble Space Telescope's capabilities and limitations. Early observations of Andromeda with Hubble revealed faint variable stars and provided better measurements of distances. These observations improved the calibration of the cosmic distance ladder, the series of observational techniques used to measure distances to
increasingly distant objects. The Cepheid variables in Andromeda observed by Hubble were particularly important. These observations improved the measurement of the distance to Andromeda, which in turn improved our measurements of the distances to other galaxies and provided more accurate estimates of the size and age of the universe. Let me discuss the specific wavelengths at which Andromeda has been observed and what each observation reveals. In radio wavelengths around 1,420 megahertz, the wavelength of neutral hydrogen emission, Andromeda appears as an extended disk of cold gas. These observations reveal the distribution of the interstellar medium and show that Andromeda has a large reservoir of gas available for star formation. In radio wavelengths corresponding to 21 centimeter radiation, Andromeda shows asymmetry between its approaching and receding sides. The Doppler effect causes emission from the side of Andromeda moving toward us to be shifted to slightly shorter wavelengths, while emission from the side moving away is shifted to longer wavelengths. This asymmetry provides information about Andromeda's rotation and its motion relative to us. In the infrared, particularly at wavelengths around 10 to 30 micrometers, Andromeda shows emission from dust heated by starlight. These observations reveal the distribution of dust in the galaxy and allow astronomers to map star formation that would be obscured by visible dust. In the sub-millimeter range, wavelengths of about 100 to 1,000 micrometers, Andromeda emits cold dust radiation. Sub-millimeter observations reveal the coldest dust, which is often associated with star-forming regions. In visible light, wavelengths of about 400 to 700 nanometers, Andromeda shows the distribution of stars and the dust lanes that obscure background stars. In ultraviolet light, particularly at wavelengths shorter than 200 nanometers, Andromeda shows its most active star-forming regions. The young, hot, massive stars that form in these regions emit copious ultraviolet radiation. In X-rays, Andromeda shows point sources, mostly binary star systems and possibly a pulsar or two, and diffuse emission from hot gas in the outer regions of the galaxy.
By observing Andromeda across this entire spectrum, from radio waves to X-rays, astronomers build a complete picture of the galaxy's structure, composition, and physical processes. Each wavelength reveals different aspects of the galaxy that wouldn't be visible at other wavelengths. Let me discuss some of the parallels between Andromeda and our own Milky Way galaxy. Both galaxies are spiral galaxies with disk and bulge components. Both have halos of dark matter extending far beyond the visible disk. Both contain supermassive black holes at their centers. Both contain billions of stars and vast amounts of gas and dust. Both have satellite galaxies orbiting them. Yet there are also differences. Andromeda is larger, about twice the diameter of the Milky Way. Andromeda's supermassive black hole is much more massive, 140 million solar masses versus 4 million solar masses. Andromeda has more globular clusters. The Milky Way has more prominent satellite galaxies like the Magellanic Clouds. These similarities and differences are valuable for comparing the two galaxies and learning how galaxy properties vary. By understanding why Andromeda and the Milky Way differ in certain respects, we learn about the factors that influence galaxy evolution. The comparison also raises interesting questions about the future. Will the merger of the two galaxies be symmetric, or will one galaxy substantially absorb the other? How will the final galaxy's properties depend on the properties and configurations of the two galaxies before the merger? Simulations suggest the final galaxy will be dominated by a massive elliptical shape, but details depend on the exact dynamics of the merger. Let me conclude with some final thoughts about the profound significance of Andromeda in human understanding and experience. Andromeda represents the cutting edge of human knowledge and observation about the universe. The fact that we can observe a galaxy 2.5 million light years away, determine that it contains a trillion stars, understand its structure and composition, and predict its future merger with our own galaxy, this represents an extraordinary intellectual achievement. This achievement was built over centuries through the work of countless astronomers who built better
telescopes, developed more sophisticated theories, and made careful observations. Each generation of astronomers added to the understanding that Andromeda eventually revealed to us. Andromeda also represents the continuation of an ancient human impulse to look up at the night sky and wonder. This impulse goes back to our earliest ancestors. The fact that modern science has transformed this wondering into detailed knowledge doesn't diminish the fundamental human curiosity that drives it. For each person who looks at Andromeda, whether through a telescope or binoculars or simply with naked eyes from a dark location, Andromeda can be a window to the cosmos. It can inspire wonder about what other worlds might exist in those trillion stars. It can provide perspective on the scale of reality. It can be beautiful and awe-inspiring simply as a spectacular sight. Andromeda is waiting for you. It's there in the night sky, visible to the naked eye from a dark location, waiting to be observed and appreciated. Whether you observe it with sophisticated equipment or simply with your eyes, whether you study it scientifically or enjoy it aesthetically, Andromeda will reward your attention with genuine beauty and genuine wonder. The story of Andromeda, how far it is, what it contains, the galaxies it has consumed, the collision that awaits in the future, the light that has traveled for 2.5 million years to reach us, is one of the great stories of the universe. It's a story of scale, of time, of cosmic processes operating on timescales and distances that dwarf human experience. Yet understanding this story, learning about Andromeda, helps us understand our place in the cosmos. We live in a galaxy. Our galaxy is part of a local group. Our local group is part of a supercluster. Our supercluster is part of the universe, and our universe is just one galaxy among billions, or perhaps one universe among countless universes in a multiverse we can barely comprehend. Andromeda reminds us of this cosmic perspective. It reminds us that we're not at the center of anything, that our concerns and problems, however important they seem, occur against a backdrop of immense cosmic processes. This can be humbling, but can also be liberating. It can help us see beyond our immediate concerns to larger questions and grander perspectives. Let me make a final observation about Andromeda that deserves special attention. Every single object you can see in the night sky, every star, every nebula, every galaxy is made of the same fundamental particles as you are. The atoms in your body, the iron in your blood, the calcium in your bones, the carbon that forms the backbone of your DNA. All of these elements were formed in the cores of stars. When those stars exploded as supernova billions of years ago, those atoms were scattered into space. They were incorporated into new clouds of gas that formed new stars and planets. Eventually, those atoms became part of Earth, and eventually, part of you. This means that you are not separate from the cosmos. You are part of it. You are made of the same material as everything else in the universe. When you look at Andromeda, you're looking at a galaxy made of the same stuff as you are. You're looking across an immense distance at a physical structure that shares your composition. This is profoundly true. It's not metaphorical or poetic. It's literal physical truth based on our understanding of stellar nucleosynthesis, the nuclear reactions that occur in the cores of stars that create heavy elements. Every atom in your body older than about 1 billion years came from a star. The hydrogen you're made of was created in the Big Bang, but the heavier elements, oxygen, carbon, nitrogen, calcium, iron, were created in stars. The Andromeda galaxy contains trillions of these star-forged atoms. When we observe Andromeda, we're observing a vast collection of atoms. These atoms have been assembled by gravity into stars and planets and galaxies. They follow the laws of physics just as your atoms follow the laws of physics. This creates a profound connection between you and Andromeda. You and Andromeda are part of the same universe, governed by the same laws. You're both made of the same stuff. The only difference is organization and scale. This perspective, understanding that you're not separate from the cosmos, but intimately connected to it, can be transformative. It can change how you think about yourself and your place in the universe. It can inspire awe and wonder at the physical laws that govern everything. The more you learn about Andromeda and the universe, the more you realize that the universe is rational, comprehensible, and deeply interconnected. The same laws that govern the orbits of stars in Andromeda govern the orbits of electrons around atomic nuclei in your body. The same gravitational forces that hold Andromeda together hold the Earth and Moon in their current configuration. Understanding these connections doesn't diminish the wonder or beauty of the universe. If anything, it enhances them. When you look at Andromeda, knowing that it's made of the same material as you, that it follows the same laws of physics, that you and Andromeda are connected through a vast network of causation and physical interaction spanning billions of years, this knowledge makes Andromeda even more beautiful and profound. The study of Andromeda is, in a very real sense, a study of ourselves. When we understand how Andromeda formed, how it evolved, what physical processes shape it, we're learning about the physical laws that also shaped us and govern our existence. This is the deepest significance of Andromeda. It's not just a distant galaxy that's interesting to observe and study. It's a connection to the fundamental nature of reality. It's evidence that we live in a universe governed by comprehensible physical laws. It's a reminder that we're part of something vast and eternal. As we conclude this exploration of Andromeda, let me address one final question. What's next for Andromeda observations? The upcoming decade will bring revolutionary new capabilities for observing Andromeda and other galaxies. The James Webb Space Telescope is already revolutionizing our understanding of the early universe and nearby galaxies. Future infrared observatories will probe even deeper into Andromeda's structure. The Nancy Grace Roman Space Telescope will provide unprecedented views of nearby galaxies and will be able to resolve individual stars across much of Andromeda. This will allow astronomers to create the most detailed census of Andromeda's stellar populations ever achieved. Ground-based telescopes under construction, the extremely large telescope in Chile and the 30-meter telescope in Hawaii, will have resolution approaching or matching space telescopes for certain observations. These ground-based observatories will be able to study Andromeda's nucleus in unprecedented detail and observe individual stars in Andromeda from the ground. Radio telescopes continue to improve. The Square Kilometer Array, when complete, will be thousands of times more sensitive than current radio telescopes. It will be able to detect subtle signals and structures in Andromeda's radio emission that are currently invisible. Gravitational wave detectors like LIGO might eventually detect gravitational waves from distant supernovae in Andromeda or from other events in the galaxy. This would open a new window on Andromeda, allowing us to observe events through gravitational waves rather than just electromagnetic radiation. Neutrino detectors might detect neutrinos from supernovae or from other processes in Andromeda. Neutrinos pass through ordinary matter almost unimpeded, carrying information from the cores of stars and the centers of supernova that would be obscured to ordinary telescopes. Each of these new tools will expand our understanding of Andromeda. Each will reveal new details and answer old questions while raising new mysteries to investigate. The study of Andromeda will never be complete. There will always be new observations to make, new questions to ask, new mysteries to explore. Andromeda will continue to teach us about galaxies, about stars, about the processes that shape the cosmos. In the billions of years until Andromeda collides with the Milky Way, there's plenty of time for further discoveries. If intelligent life survives on Earth during those billions of years, if humanity or its descendants or some entirely different civilization continues to exist and observe the cosmos, they will continue to study Andromeda and learn from it. Perhaps by that time, when Andromeda is visibly growing larger in Earth's sky as it approaches, observers will have a much more complete understanding of the galaxy. They will have made observations with telescopes and techniques we can't yet imagine. They will have answered questions we don't yet know how to ask. Yet I suspect they will also feel the same awe and wonder that we feel when we look at Andromeda now. There's something about looking across millions of light years to observe a distant galaxy that transcends specific scientific questions. There's something about recognizing that you're observing something vast and ancient and magnificent that touches something deep in the human spirit. That awe and wonder, that sense of connection to something larger than ourselves, something older than human civilization, something grander than our daily concerns, is perhaps the most valuable legacy of observing and studying Andromeda. As long as humans exist and are capable of wonder, Andromeda will inspire that wonder. It will draw our gaze outward to the cosmos. It will remind us of our connection to the universe and our place within it. It will encourage us to ask questions, to pursue knowledge, to expand our understanding of reality. That is the true significance of Andromeda, not just as an object of scientific study, but as a source of wonder and inspiration for the human spirit. Let me make one final personal reflection on Andromeda. The first time I learned about Andromeda, really understood it, not just knew the name, but grasped what it meant, I was changed. I realized that I lived in a universe far grander than I had imagined. I realized that I was connected across millions of light years to a distant galaxy containing trillions of stars. I realized that the universe was not a static backdrop for human existence, but a dynamic system of immense complexity and beauty. This realization didn't make my personal life less important or meaningful. If anything, it enhanced meaning by connecting my life to something larger. I realized that I was part of a cosmic story, that the atoms of my body had been forged in stars, that I was observing the universe through the gift of consciousness. This is what Andromeda offers to everyone who takes the time to look at it and think about it: a sense of connection to the cosmos, an understanding that we're part of something vast and eternal, a motivation to expand our knowledge and appreciation of reality. If you've never observed Andromeda, I encourage you to do so. Find a dark location away from city lights. Wait for your eyes to adjust to the darkness. Then look for the constellation Andromeda in the fall and winter sky. Look between Cassiopeia and Pegasus. You'll find a fuzzy patch of light. That's Andromeda, the most distant object visible to the naked human eye. That's a galaxy containing over 1 trillion stars, 2.5 million light years away, moving toward your galaxy at tremendous speed, doomed to merge with the Milky Way billions of years in the future. Take a moment to really think about what you're looking at. You're looking across an immense distance and backward through immense time. You're observing one of the major structures of the observable universe. You're participating in a human tradition of observation and wonder that goes back centuries. That experience, that moment of genuine connection with the cosmos, is worth seeking out. It's worth the effort to find a dark place and look up at the sky. It's worth taking the time to appreciate the beauty and wonder of the universe. Andromeda is waiting for you. It's there in the night sky, eternal and patient, ready to inspire wonder in anyone who takes the time to observe it and contemplate its significance. Let me end by considering what Andromeda will mean for future generations. Long after we are gone, Andromeda will still be there. It will be growing brighter and closer as it approaches a collision with our galaxy. It will be visible in the night skies of descendants of humans, or of whatever species replaces us, or of whatever conscious observers may exist in this region of space billions of years hence. Those future observers will look at Andromeda and feel the same sense of wonder that we feel. They will see a galaxy of unimaginable scale containing trillions of stars. They will understand, as we do, that they are looking at something vast and ancient and magnificent. They will feel their own smallness against the backdrop of the cosmos. And perhaps they will think back to us, to the humans of the 21st century who looked at Andromeda and tried to understand it, who built telescopes to observe it, who wrote about it and thought about it and marveled at it. Perhaps they will recognize that we were part of the same human story that extends across billions of years, the story of conscious beings seeking to understand the universe. That continuity, the idea that wonder about Andromeda connects us across billions of years to future observers. is perhaps the most profound thing about Andromeda. It's not just a galaxy, it's a connection between the past, the present, and the future. It's a symbol of the enduring human impulse to seek knowledge and understanding. In billions of years, when Andromeda is close enough to see obvious structure in the merger process, the night sky will be transformed. Two galaxies will be visibly merging. The stars that were fixed features of the night sky for billions of years will begin to shift and move as the gravitational dynamics of the merger rearrange them. Those future observers will know, as we know now, that this merger was inevitable, that it was predicted by the astronomers of our time based on Andromeda's motion toward us. They will look up and see this prediction fulfilled, this cosmic drama playing out across their sky. They will be witnessing one of the most spectacular events possible in the cosmos, the merger of two galaxies. We live in the time before this merger. We have the privilege of knowing it will happen, of understanding the physics that makes it inevitable, of observing the two galaxies as separate entities before they combine. This is a remarkable position to be in. We are observers of the cosmos in an era when major cosmic structures are about to undergo profound transformation. This knowledge enriches our experience of the night sky. Every time we look at Andromeda, we can think about the future merger. We can contemplate the vastness of the timescale involved, 4.5 billion years, which seems incomprehensibly long, yet represents just one small chapter in the history of the universe. Andromeda teaches us that we live in a universe of immense beauty and complexity, governed by physical laws that we can understand and describe. It teaches us that our position in space is not central or special, that we are inhabitants of an ordinary galaxy among billions. It teaches us that even though we are small and temporary on cosmic scales, we are still part of something vast and eternal. In the final analysis, Andromeda is a story about perspective. It's a story about how we understand our place in the cosmos, about the journey from ancient observers who saw only a fuzzy patch in the sky to modern astronomers who can map the structure and dynamics of an entire galaxy containing 1 trillion stars. Andromeda reminds us that the universe is far grander than any individual human life, yet that individual human curiosity and intelligence can comprehend the universe and discover its secrets. We are the universe observing itself, conscious matter reflecting on the larger cosmos from which it emerged. Every observation of Andromeda, every measurement, every photograph, every scientific study, all of these represent humanity asserting our ability to understand the cosmos. These are acts of courage and wonder in the face of an incomprehensibly vast universe, an expression of our deepest desire to comprehend reality. That is the ultimate significance of Andromeda. It is a testament to human curiosity, to the power of observation and reason, to our capacity for wonder in the face of cosmic grandeur, to our ability to reach out across millions of light years and touch the stars. Thanks for watching.